Our paper, the MTM-EBG as a rigorous multiconductor model of the UC-EBG and approaches for miniaturization, proposes and examines a new multiconductor circuit model that better approximates the behavior of this famous structure's multiple modes over previously proposed equivalent circuit models. The uniplanar compact electromagnetic bandgap structure, or UC-EBG, also known as the uniplanar compact photonic bandgap structure, or UC-PBG as it was originally known, was proposed in the late 1990s with applications to noise suppression in microwave circuits, decoupling of antennas, and waveguide miniaturization, among others. Since that time, it has found a variety of other applications, from filters to metasurfaces. Historically, the UC-EBG's behavior has been modeled as a simple LC resonator, comprised of a current loop containing capacitance between the gaps of adjacent periods, and inductance in the form of thin strips connecting these periods. When observing the fields of some of the modes produced by a full-wave numerical eigensolver, we noticed that these field profiles corresponded to canonical transmission line modes such as coplanar waveguide, or CPW, coupled slot line, or CSL, microstrip, or MS, and others, which we had previously observed in a one-dimensional EBG developed in Professor Iyer's research group. This structure, the metamaterial-based EBG, or MTM-EBG, was shown to support three quasi-TEM propagation modes, which were identified as CPW-like, MS-like, and CSL-like. The observed similarities of the field profiles between the two structures led us to conclude that the MTM-EBG could serve as part of a more sophisticated multiconductor model for the UC-EBG, which aside from accurately predicting the bandgap frequencies, could also well model many of the properties of the unit cell's block modes. We hypothesized that four MTM-EBG structures could be arranged in an intersecting fashion, along two primary rectangular axes. In this case, the loading inductors of the MTM-EBGs would be placed connecting the outer smaller squares of the UC-EBG with its central nodal region, where we observed higher current densities associated with physical constraining of the currents, implying inductive behavior. The loading capacitors of the MTM-EBG would remain as they are in the simplistic UC-EBG model, created by electric fields joining adjacent unit cell edges. Solving the dispersive properties of the resulting circuit model yields the solid curves shown in this figure. These results are in relatively close agreement with the full-wave eigenmode solutions of the corresponding physical model from HFSS, given by the dotted curves. Finally, the work details the miniaturization of the UC-EBG through the introduction of much more sizable reactive loading components, in particular the series loading capacitors. With increased loading, it is found that the circuit model produces data exhibiting even better agreement with HFSS while retaining the UC-EBG's desirable dispersion properties, opening an avenue for rapid simulation and substantial miniaturization of this canonical EBG structure.